So what I'd like to tell you about, this was my PhD student's work who graduated about a year ago, Evan Cooper-Smith. He's now at the USDA Hydrology and Remote Sensing Lab out in Maryland, continuing this work. And at that time, John Deere was at kind of a critical point where they were trying to figure out, do we make machines or do we make data or do we make both? And there was kind of some internal warfare going on there. We have John Deere Technology Innovation Center is located on the University of Illinois campus in our research park. And so we were fortunate enough to have some folks there. I'm a water resources engineer. This was my first project in the ag arena. So it was very much a strong partnership with John Deere. They funded it, but they also met with my student every week. My students spent, entire summers in their offices immersed in understanding what their issues were. And so they were having this battle going on and trying to do, so this was exploratory work to say, well, if we were a data company, what data would we work with and how would we do it? And we envisioned when we started that we were going to focus on, let's see, this is going to work, on the machines, because with all the technology that's on the machines now, they generate an enormous amount of data, but mostly it sits there on the machines and is not actually harvested to do anything. In the end, though, there's a lot of privacy issues with working with farmers' data that they've been generating, and Deere wasn't quite ready to step into the space of asking their customers to give them data back. They're doing it on a small scale now, and I think in the next couple of years, I have a new student starting in August who's finally gonna get that data off some of the machines that we're gonna start working with. But so we started from the perspective of what could we do with publicly available data and use that to feed back to the farmers to provide them information as to what's the best thing to do now. And we were thinking about the two extremes here. So one where the field is so wet and you don't want to take your machine out in this kind of condition where it's just going to wallow and sink in the mud and cause all kinds of damage both to the field and to the machine itself, as well as the opposite extreme of drought, where we're having in climate resilience more of these two extremes where it's really wet or it's really dry. And when is it time to perhaps put some irrigation in? When is it time to sit and wait and maybe put more drainage in or more carbon to capture the water, given the last talk? So we started with the left-hand problem of too wet and started out saying, well, let's look at field readiness. When is a field going to be ready to be worked? When is it dry enough? And just given some input about how much rain has fallen in an area, could we predict the field readiness? And field readiness was just a quantitative scale from 1 to 5 that an expert could go out in the field and look at it and say, yeah, that field's ready to be worked, or no, it's not. And as we have larger and larger farms, we were hearing about services where they're actually driving 500 miles in a day to go around and inspect the fields and decide which ones are ready to be worked. And could we do that remotely and perhaps save a lot of greenhouse gas emissions in that driving? So this was a machine learning exercise. We were trying to train the computer to tell us, is this field ready or is it not ready based on the rainfall input alone? We were looking at the South Farms in Urbana because it was very easy to send an intern out to make the assessment. This was a young man who came out of a farm family, and he went out there and he made his assessment as to whether a field was ready to be worked or it wasn't every single day for the entire summer. And then we took that information and the rainfall data from the Illinois Climate Network, as well as NEXRAD radar data, and we had some other data we worked with from ICN as well, in terms of humidity and evapotranspiration. And some soil sensor locations, soil moisture locations, which we used as our benchmarks as well to compare soil moisture with this field readiness measure. So the way this worked then was we had our field readiness data from this intern. We had the precipitation and potential evaporation from the Illinois Climate Network, and we had the NEXRAD data, which was, these data were daily. NEXRAD is delivered at much higher frequency. The data come together, and we use 3 different approaches to train the predictions: a boosted perceptron, regression trees, and K-nearest neighbors to create the nowcast. And I'm not going to spend a lot of time on what those different types are, but if anyone's interested, I can give you more information. And we looked at how well do the human and the computer compare? How well can we train the computer to predict whether the field is ready or not? And with the classification tree, this is the K-nearest neighbors, which basically in a K-nearest neighbors, this one did the best. You're simply going back and looking historically and saying, given the conditions I'm seeing today, let's look historically at all the days that were most similar to this day, and then how often was the field ready under those conditions. So it's a fairly simple concept of let's just use the past to try and historically see how close we are. The nice thing about that is as conditions change over time, as climate changes, you can continue to change your model because conditions will change and that historical base will change over time. And then we looked at, this is for that KNN that did the best in terms of predicting compared to the human. We said, so here's the green dots are when the human said the field is ready, and the red dots are when he said the field was not ready. So you see that there's, we said 1 and 2 are not ready, 3, 4, and 5 are ready. We took out all the examples when it hadn't rained within 3 days, because that was kind of a no-brainer. At that point, obviously, the field is ready if it hasn't rained within 3 days. These are tile-drained fields in central Illinois. They drain very quickly. And what happened, so here's that line between not ready and ready. So we're not trying to predict the actual class, just whether it's ready or not ready. Here's what the computer did, the green and the red. So you don't want to look at how close is this in the actual number, but rather how often do the greens match and how often do the reds match. Where there were errors, those happened. So right here, we did quite well. They were both green. Here's where an error happened. The human said it wasn't ready. The computer said it should be ready. And whenever that happened, it was when the human assessment was 2 or 3, which is kind of borderline ready. And that's where the errors were occurring. And we could actually create an error band around the computer model predictions and see those error bands that our predictions were all included within those error bounds. The actual interns' assessments were included within the error band predictions of the models. So if we use those error bands, then we can do pretty well. So that's where we started, was what can we do at this one site? But then the problem was we didn't have farmers around the country to tell us when the field was ready as a training data set. We didn't have interns around the country who could do that. So then we said, well, maybe we should move to soil moisture, because there are soil moisture sensors around, and we can use that as a proxy for when the field is ready. And then the question became, well, there are soil moisture sensors in some places, but not everywhere. Not every farmer has them. So can we figure out a way that, given a soil moisture assessment in one place, we can say, what does that mean is going on in other places? And that was what we set out to do. So we started out with a kind of a simple physics-based approach, and then overlaid on top of that a machine learning model. This is called the Diagnostics Soil Moisture Equation by Panadal in 2012. And so we started with this. It includes soil moisture losses due to evapotranspiration, drainage, and it assumes they can be estimated by a sinusoidal function that takes 3 parameters to do that. Here's the different parameters and how it shifts as you add each one, and you wind up with a function that looks something like this. Then, so here's our function. There are 3 more parameters, so we fit those first 3 parameters with a genetic algorithm, which I won't go into those details. And then we had a second genetic algorithm that took the observed soil moisture values and a loss function. And so that brings in the permeability and the loss, and we wind up with this equation that's an analytical function to estimate soil moisture. The next step then, this is my students' details, which I'm not going to get into, was to add to that a machine learning model that would do some error correction. And we took some soil moisture time series from different locations around the country. Here, this one is in New Mexico, and we can see how the soil moisture varies over time when we just took the initial Panadal model. Here's the fit that we get to what was actually measured. And then we do the error correction, which is where we basically train a machine learning model to fit the error that's remaining from this Panadal equation. And it moves down much closer to where the data are, and here's the R-squared moving up some. So he did that in several different sites to put those 2 pieces together and come up with a prediction of soil moisture. So now we've got a way we can model soil moisture at locations where we have soil moisture sensors, but we still don't know what to do at all these farm fields where we don't have them. So the next step was a hydrologic classification to look at different watersheds and say, how similar are these watersheds? And if I'm in a watershed that has a soil moisture sensor and there's another one that's similar, then maybe I can use that soil moisture feed to predict what might be going on in my watershed where I don't have one. So that was the next step of his work. He looked at 4 different features for classifying watersheds, and he worked with a data set of, I think it's about 420 different watersheds around the country that have a lot of good data about soil moisture. So the 4 different features that he focused on, he tried a whole bunch of them, eliminated others, were seasonality, aridity, maximum precipitation, timing, when is the rainfall the highest, and then the 4th is the maximum runoff timing. So you get basically these 4 different signatures of a watershed of how quickly does soil moisture change in this watershed because of these different features. The one you'll see that isn't in here that people always bring up is topography. I'm going to come back to that later. So taking that, he built a classification tree that basically took all these watersheds, these are all the watersheds around the country that we worked with the data, and split it into different classes. And a classification tree starts at the top, all the watersheds are together, and then you split them into different categories. And the first split is the one that had the highest predictive capacity because it was most correlated with soil moisture. So seasonality was the first one that came up. And the less seasonal east got separated from the more seasonal west. So that separation is done through the algorithm. We're not actually explicitly doing it. It's training to fit the data the best. The second split then went on rainfall timing, And then we get more of the aridity breaking out. Then the third split continues, and you start to see these other clusters of watersheds emerge. And in the end, there were 24 different classes. These are the 428 MOPEX catchments. So MOPEX is the name of the data set. And there were actually only 6 classes that described over 77% of the 428 catchments. So now we take these classes, and with that, we could say, well, if we had a sensor here in this yellow zone, a soil moisture sensor, and we wanted to predict what was going on someplace else in another yellow zone, perhaps we could see if we can do that with this kind of approach. Got a bunch of graphics my student put in here that I'm going to skip through. He's showing you where some of these different classes are. He likes animations. But we then came to the question when he started working with these data, he noticed that the data seemed to be changing over time. It was about 50 years worth of data, and he decided to try splitting it into pre and post 1975 is where he started, and then he actually tried 1980 as well as another year that he split on to see if that made any difference. And what was happening in these catchments before and after that date, and would we see signatures of non-stationarity of this climate change happening in these watersheds, and what would that say about how we do these kinds of predictions of what might be going on? So again, went back to that same classification tree to classify these different watersheds, but now separating and doing it once before 1975 and once after 1975, and then seeing which watersheds were shifting classes during that time. So here's what the different watersheds look like before. This was actually the 1980 split. And we see the different high seasonality and aridity in the red, high seasonality and humidity in yellow, low seasonality and early precip versus late precip in these two different blue ones. And watch with your eye what's happening right here in the Northeast. After 1980, we see a shift where there's a whole lot more watersheds here that are now being classified in the dark blue rather than the light blue. And the light blue, he's got 2 different dark blues there. There's a typo there. How did we let him graduate? Okay, so, but we're shifting in terms of the timing of the precipitation from early to late with a shift from light blue to dark blue. So the precipitation is shifting later. And we can see this in different regions of the country. These are those different indicators that I talked about. And the red is pre-1980, and the blue, no, sorry, the blue is pre-1980, and the red is after 1980. So these are the 2 different indicators that we're tracking in this classification system. And here in the Midwest, where we're located, we see a shift in the peak runoff. This is the runoff track down here in the bottom. We also see higher low flows. In the Pacific Northwest, we see a little bit different trend where, because we have diminished snowpacks, we see that the runoff is diminishing during these months. But the winter runoff is pretty much unchanged. So these are just signatures that we're seeing in the data. In the Rocky Mountains, we see smaller snowpacks as well. So all the mountainous regions, we could see the signature of the smaller snowpacks happening after 1980. We also see in the rainfall, which is the upper one, steadier rainfalls happening. In the Southeast, we can see after 1980 significant drop in rainfall trend happening there. So systematic drying happening in the southeast, which is where we see those droughts starting to pop up more. So when we think about what are the implications of this kind of thing for agriculture, maybe in the southeast will be the place where there needs to be more investment in irrigation equipment to address some of these, more investment in some of these conservation practices to be capturing the moisture and holding it more, starting to get more creative about how we're going to work with water. In the more mountainous areas, the lack of snowpack is going to be more and more of an issue. So how are we going to address that? So we can look for different trends of what does this mean from a management perspective. So now, the next question was, could we use this kind of classification system to then say, here's my farm field, I want to know what's going on, how dry is it? I don't have a soil moisture sensor there, so can I use a proxy from somewhere else using this kind of classification system? And that was the last piece of his work, and the answer was yes. So what we did was to look at these different watersheds again, and we started with different pairs of watersheds, and we took, if we take one watershed and try to predict soil moisture and another one, if those two watersheds were in the same class, then that's the green set. If the two watersheds were in unrelated classes, that's the red watersheds. If they were differed by only one split on this classification tree, then that's the yellow watersheds. And so these are the errors that we saw in trying to make that prediction from a place, from one watershed to another. And you can see that the errors are significantly lower in the watersheds where the pairs came from the same classes. If they were closely related, we do a little bit better, but if they're from completely different classes, then we don't do well at all. So that was a nice finding to see that we can do some generalization from one site to another. What we really wanted to do, and let me summarize the whole process then. We start with Panadol. We use the Soil Climate Analysis Network, that data, to say what's going on at this particular field. We generalize via this classification to understand what's going on nationally in similar sorts of watersheds. Do our cross-validation to see that that worked pretty well. Where we want to go in the future, and this was what we were always hoping to do, but we were never able to get the data, is how does topography play out in this? Because if you look at a farm field, even a flat farm field, it's got a lot of variability. Some areas have, some slight hillocks to them, others do not. These areas at the top of the hill are going to dry a lot faster than these areas down in the hollows, and you can see this happening in farm fields. We have information off these machines to know what the detailed topography is, and even to know how much yield are they getting off of these different areas. And so maybe we can move to a point where we can plant different types of seeds in areas that dry faster versus areas that dry slower, and irrigate in different ways at a very field-specific level, much more fine-tuning of how we're managing these systems. So that's the next step that my student will be starting in August, is to bring in this topography feature and then go from national scale, okay, we know this area is generally like this, and we've got a soil moisture sensor in the area. Now let's take this very localized data and say, what does that mean about what I should be doing on my field today? Lots of animations. Okay, so here's our model. So here's where we could go with this, and this is what Evan's working on in his postdoc now, is this new SMAP data, soil moisture data coming in. It's at kilometer scale, so it's pretty large scale stuff. But how might that play out into this? We've got the radar data, which is what he worked with. It's also at kilometer scale. And we've got LIDAR data, which is at meter scale, where now we're gonna have information coming off the machines that are at even finer scales. How are we gonna put all these scales together? I think there's a lot of really exciting possibilities for where we can go with this in terms of improving how we do management practices in agriculture and practice them in a way that will be more resilient to these changes that are happening. When we see these watersheds that are shifting from one class to another, are becoming more arid, are becoming more higher peaks of wet and dry. So I'm very excited about the possibilities of where this is going, and anticipate this partnership with John Deere continuing with this new student, and we'll see where it's going to go. Right now, I'd say the data battle has been won at Deere. They now have a data group and a senior executive who's been appointed to oversee the data and how they're going to deal with it. So they have decided that they are about data as well as hardware. They still haven't quite figured out exactly how to do that. So a lot of interesting possibilities for where it goes. And I'll stop there. Thanks.